Hey everybody, Mrs. Pesic here.
And Miss Bella here.
And we're looking at section 10.3 on the unit circle. The objectives are to convert angle measures between degrees and radians and to find the values of the trig functions on the unit circle. So your vocabulary, radian and unit circle. So far you've measured angles in degrees, but you can also measure angles in radians. What is a radian, you might ask? It is a unit of angle measure based on arc length. So recall from geometry that an arc is an unbroken part of a circle. So for example, from here to here, that might be an arc of the circle, all right? It actually is an arc of the circle. If a central angle theta in a circle of radius r intercepts an arc of length r, then the measure of theta is defined as 1 radian. So let me slide my picture down here. So in other words, if the radius of the circle is r, and here's our angle, theta, okay, and if this arc length right here is also r, that means that theta must measure 1 radian.
Okay, so when we talk about circumference of a circle of radius r, we would say it's 2 pi r. So that means that if you go all the way around the circle, there are 2 pi radians, or of the length of the radius. So therefore, an angle representing one complete clockwise rotation measures 2 pi radians. So you can use the fact that 2 pi radians is equivalent to 360 degrees to convert between radians and degrees. So again, if you take a look at our picture up here, we'll make that a little bit bigger for us. In here, we have in blue, that measure is half the circle, so halfway around here. Well, half of a full circle is 180 degrees, or we would say that that is pi radians. Remember pi, 3.14 approximately, so that's how many radians our angle would measure. If you go a full circle all the way around, well, in degrees, that is 360 degrees, so that angle theta would be equivalent to 2 pi radians. So that again means that when I'm thinking about a circle, okay, that circle, and you start here and you measure out what your radius would be. So how many of those measurements could you do all the way around to make it all the way around the circle? You're going to find out that there would be 2 pi of the radius measures.
So about 6.28 of those radian measures all the way around the circle. Okay, so that means that if you want to convert from degrees to radians, you just need to multiply the number of degrees by pi radians over 180. And if you want to convert from radians to degrees, it's just the reverse. You'd multiply by 180 degrees over pi radians. Let's take a look at an example. So convert from degrees to radians or from radians to degrees. In this case, we're going to convert negative 60 degrees. And you could maybe use a little T-chart idea here, because we're going to multiply by pi radians over 180 degrees. The degree units divide out, and we can say that 60 goes into 60 once and into 180 3 times. So it looks like we end up with a negative 1 times pi over 3. So that's going to be a negative, we're going to write this as negative pi over 3 radians. All right, what about converting the other way? What if we've got 2 pi over 3 radians and we want to convert that to degrees? Again, if we make a little T-chart here, we can say we want to multiply by 180 degrees this time over pi radians. Radians divide out, leaving us with degrees as our unit. And I can see here that this pi is going to divide out with this pi, so I end up with 2/3 times 180. 3 goes into 3 once, and 180 60 times, so 2 times 60 gives me 120 degrees. So 2 pi over 3 radians is equivalent to 120 degrees.
So when we're taking a look at this, angles measured in radians are often not labeled with the unit. If an angle measured does not have a degree symbol, you're going to automatically assume that that angle is measured in radians. So for your first must do here, doing that conversion again for A, you're going to convert from 80 degrees and change that into radians. And in B, you have 2 pi over 9 radians, and we'd like to change that into degrees. So again, use that chart and kind of cancel out the units like we just did in the last example.
So we're looking for an answer for part A as a fraction.
Correct. Yeah, leave it. Do not multiply the pi out. Leave the pi in your answer. All right, now, how is this all going to help us? And I know we've kind of mentioned a little bit about the unit circle, but here it actually is. So a unit circle is a circle with a radius of 1 unit. So for every point xy on a unit circle, the value of the radius is 1. So therefore, an angle theta in the standard position, so finding its sine, cosine, or tangent, can be represented by the x value, the y value, and then the radius of whatever that would be. The radius, anytime you see an r in this case, the r is always going to equal 1 because that's how a unit circle is defined. So take a look at our unit circle over here. From the center out, so the radius there, that's probably one of the easiest ways to see it, that is 1. So you'll notice that ordered pair is 1, 0. Again, 1 unit up, so 0, 1, 1 unit to the left, and 1 unit directly down on the y-axis. Every space on that circle has a radius of 1, and we are given both the angle measures for these in degrees and radians, as well as what ordered pair that would hit on the circle. We talked a little bit about special right triangles, and that's actually where these ordered pairs are coming from. What is the x-coordinate and the y-coordinate? You know, kind of if I were to draw in a triangle here, for example, so that was the 30. So if this was a 30-degree angle, this ordered pair would be my x and my y coordinate for that triangle. So we have these ordered pairs. We will give you this circle filled in. I know we mentioned that next year in trigonometry, then you'll need to memorize where these values come from.
Okay, so the coordinates of any point on the unit circle can be written cosine theta, comma, sine theta. So for example, if we have the point here for 4 pi over 3, we could say that the cosine of 4 pi over 3 is going to be the x-coordinate of that point. So the cosine is going to be negative 1/2, and the sine of 4 pi over 3 is going to be the y-coordinate at that point. And we can see the y-coordinate is negative square root of 3 over 2.
The diagram is going to show the equivalent degree in radian, as we mentioned, of the special angles and their x and y. So we're going to use this unit circle to do some follow-up questions, and we'll always reference back to it as we're answering our questions. So we're going to use the unit circle to find the exact value. Again, that means no calculator here. Exact value of each trig function. So from what we just talked about, the cosine of an angle is always going to be its x-coordinate. So if I take a look at the angle I'm given, 225 degrees, my first step is to look on my unit circle and find out where do I see 225 degrees listed. Well, that happens to be down here in quadrant 3, which would make sense. It's between 180 and 270. And I'm going to look at the ordered pair that goes with that. The cosine is the x-coordinate, so my cosine is going to be the x-coordinate right there. So the cosine of 225 degrees will equal negative square root of 2 divided by 2.
And that 225 degree angle, don't forget that that is, we're talking about this angle that looks like this. All right. So the angle theta in this case is 225 degrees. It ends up right here at this ordered pair. That ordered pair is negative square root of 2 over 2, comma, negative square root of 2 over 2. All right, let's take a look at another example. Can you use the unit circle to find the exact value of tangent of 5 pi over 6? So if we're looking for 5 pi over 6 on our unit circle, we see 5 pi over 6 is right here, and that means that that angle that we're talking about looks like this. So there's the angle that is 5 pi over 6. We see the ordered pair is negative square root of 3 over 2, comma, 1/2. So if we want the tangent of 5 pi over 6, the formula is y over r. So we want the, I'm sorry, y over x. Thank you, Ms. Bella, keeping me honest. And so the y-coordinate here is 1/2, and the x-coordinate is negative square root of 3 over 2. So if we want to simplify that, we are going to have 1/2 times, I'm dividing by a fraction so I can multiply by the reciprocal, 2 over negative square root of 3. That gives me 1 over negative square root of 3. And we don't like to leave those radicals in the denominator, so if we multiply by square root of 3 over square root of 3, we end up getting negative square root of 3 over 3. So our tangent of 5 pi over 6 is going to be negative square root of 3 over 3.
Okay, let's try another one of these. Now, sine of 315 degrees. Okay, so again, when we talk about sine of theta, that's going to be y over r, and the radius in the unit circle is always 1. So really, I'm just looking for the y coordinate. So on my unit circle, I'm going to find out where 315 degrees is. So again, my angle would be starting here, and it would be ending up down here and wrapping all the way around this way with a positive angle in that case. So my ordered pair is radical 2 over 2, comma negative radical 2 over 2. So the sine of 315 degrees will be the y value at that ordered pair, which is going to equal negative square root of 2 over 2. And let's see, let's take a look at this last one. The tangent of 180 degrees. Tangent, as Ms. Pesic did on the last one, is going to be the y coordinate divided by the x coordinate. I'm going to go ahead and find 180 degrees on my unit circle, which happens to be right here halfway around the circle. So again, that is an angle that, this goes to the semicircle there. So my ordered pair is 0, negative 1. Oh, negative 1, 0. So the tangent of 180 degrees will be the y coordinate divided by the x coordinate. 0 on top, so 0 divided by negative 1. The tangent of 180 degrees will be 0.
So the tangent of 90 degrees then would be 1 over 0. That would be undefined.
Correct.
Okay. All right, so that brings up notes must do number 2. So you're going to use the unit circle to find the exact value of cosine of 4 pi over 3. So find the 4 pi over 3 on the unit circle, and remember cosine is the x over r, where r is equal to 1 on the unit circle. Okay. Is that where we're at? I think. No. No. Wow, I just really went speeding by. Okay, so the diagram shows how the signs SIGNS of the trig functions depend on the quadrant containing the terminal side of theta in standard position. So you know that everything is positive in quadrant 1, sine is positive, cosine positive, tangent's positive, because the ordered pair here in quadrant 1 is positive, positive. In quadrant 2, you know that the ordered pairs are negative for the x and positive for the y. So that means that the cosine, which is your x coordinate, is going to be negative, sine is your y coordinate, so that's going to be positive, and tangent is going to be negative. All right, in quadrant 3, you know the ordered pair is negative, negative, so that means that the cosine is going to be negative, the sine is going to be negative, and then the tangent, since that's y over x, that's going to be a negative divided by a negative, that's going to be a positive. All right, and then lastly in quadrant 4, where things are of the form positive comma negative, cosine is going to be positive, sine is going to be negative, and tangent is going to be negative. And one way to remember this is with an ASTC, right, something like this, ASTC, and if you remember that, all students take calculus, and that's just a little mnemonic way of remembering what's positive in those quadrants. So they're all positive in quadrant 1. The sine and its reciprocal are positive in quadrant 2. Tangent and its reciprocal are positive in quadrant 3. Cosine and its reciprocal are positive in quadrant 4.
Now, another thing we're going to be able to do with this is that if we know the measure of a central angle of a circle, we can determine the length S of the arc intercepted by the angle. So again, we're going to look at this picture for a second, and I'll go back up there to the top with you for a second. So if I take a look at this circle, if I know how big my angle is, so theta right there, and you know what your radius is, so how large is this circle, you can figure out how long of a piece has been cut off by that angle. So in order for us to do this, we know that the radian measure of theta compared to the radian measure of a circle. So again, when we talk about the measure of an angle to the measure of a circle, we have this proportion we could set up. Really, here's what we need to know, kind of the gist of this information. Every time we want to find the arc length, which is S, we're going to find that by taking whatever my radius is, which is my r, and I'm going to multiply it by my angle measure. Now your angle has to be measured in radians, so no degrees. So if it's in degrees, you have to kind of convert that over. Now the way I like to think about this is kind of a triangle. So SRT theta. So I draw this triangle for myself every time I have a problem like this. So if I'm asked to find, say, what is the S, what is the arc length, well then I know I'm going to multiply my radius and my theta. If I'm asked, maybe find the radius, well, what would I do? I'm going to take my arc length divided by my theta, divided by my angle. So I like to use that triangle, so you'll see me draw that as I kind of answer a question here. So if we take a look at example 4, we have the tire of a car that is going to make 653 complete rotations in 1 minute. The diameter of the tire is 0.65 meters. So to the nearest meter, how far does the car travel in 1 second? So in order to do this, again, we're looking about how far the car is traveling, the tire is going. So I know that I'm going to be looking for my arc length. I'm going to be looking for S. So I'm going to draw my triangle again to help me out. And in this case, I know that I'm looking for what is my S value. So in order to find that, I'm going to need to take my radius multiplied by my angle, when my angle has to be measured in radians, not in degrees. So a couple things I need to find here. First off, let's start off with our radius. So we know in this case we have our tire here, and we know that the diameter is equal to 0.65 meters. Now, hopefully you remember the relationship between a radius and a diameter, that a radius is half of the diameter. So we are going to take that 0.65, and we're going to divide that by 2. So our radius is 0.325. So there's the first part of my formula. Next up, I need to find my angle measure. Well, I wasn't really given my angle measure in this case, but I was given some information about how many rotations were completed and in how long of a time. So we're going to kind of set up a unit conversion here to help us out. So I'm going to show this here and I'll kind of walk you through it. So what do we know to start off with? I know that there were 653 rotations that happened in 1 minute. Again, that's just the given information I know from my problem. How does that compare to the time frame, which is seconds, that we're going to be looking for? Well, if I want rotations to kind of cancel out here, I know that there are 2 pi radians, again, that's my goal for my angle, which happen in 1 rotation, because that's 1 full circle. So already rotation and rotation can kind of go away there. I need to go from minutes to seconds for my problem, so what's the conversion between a minute and a second? Well, in 1 minute, there are 60 seconds. Again, I'll put minutes in the numerator so that those would cancel out. So in this case, I'm left with radians per second, which will give us what our angle measure is, how fast this angle was moving. So if I multiply this across, I'm going to end up with 653 times 2 pi, all divided by 60. And my units would be radians per second. So that would be my angle measure in this case. Sure, to find out what that's equal to. 653 times 2 pi. And then we're going to take that answer and divide it by 60. Okay, so my angle is about 68.4, maybe we'll round it to. So about 68.4 radians. So we just found theta in this case.
So that's the rotation of the tire. That's the angle of the rotation of the tire every second.
Correct. So if I want to know how far did the car travel in 1 second, now to find that arc length, I'm going to need to multiply my radius by theta, by the angle of rotation in this case. So again, there's just a reminder of what we're going to do. So we're going to say, okay, that S is equal to, the arc length is equal to 0.325, the radius, multiplied by 68.4. And if we calculate that, again, we actually have that exact value on our calculator if we want to use that. So times 0.325, we'll find out that our tire traveled a total of about 22.2. And if we go back, we know that is in meters. So 22.2 meters in 1 second.
Okay, and I do think it's good to point out that when you remember that this has got to be in terms of radians, all right, the angle measure's got to be in radians, and that the arc length and the radius are always going to be the same units. All right. So if you were given that the radius was in meters, we said 0.325 meters, then your your arc length is going to be measured in meters also. All right, let's take a look at one last example. Must be British, it says and minute hand. Okay, so we'll say the minute hand on Big Ben's clock tower in London is 14 feet long. To the nearest tenth of a foot, how far does the tip of the minute hand travel in 1 minute? Again, we want to use our formula that says arc length is equal to radius times theta. So we are told the radius, and we are trying to find out how far the tip of the minute hand travels in 1 minute. Well, picture the clock. Not like that. Picture the clock. Here's the minute hand. All right, and we're wondering how long does it take for that minute hand to go all the way around the clock. All right, clockwise would be this direction, right, Miss Bella? Okay, so we know that we are given the radius. That radius is 14. Okay, and we know that the angle theta is going around 1 complete time, right? Okay, so Miss Bell and I just realized that we were talking about minute hands, not second hands. So that means, that's out of here. So that means that we didn't want to go all the way around the circle. This minute hand's not going to go all the way around in 1 minute. That would be the second hand that would do that. The minute hand is only going to be advancing how far? Only 1/60th of the whole way around the circle. So we want 1/60th of a revolution. All right? And we know that there are 2 pi radians in every revolution. So we've got 1/60th revolution that we're going to be doing, and times 2 pi radians per 1 revolution. The revolutions divide out, and we're left with 2 pi over 60 or pi over 30 radians. So that is going to be our radian measure. That's our angle measure. What was it? Pi over 30. And so in order for us to find the arc length, what are we actually trying to find here? We're trying to find just this distance, like how far is this tip of this hand moving in 1 minute. So we're trying to find this arc length. Remember, we use S for arc length. So that's going to be just S equaling 14 times pi over 30. And so if we pull up the calculator to do that, we want 14 times pi over 30. And when we do that, we end up getting 1.46. So about 1.5, what units are we talking about here? Feet, 1.5 feet. So it's approximately 1.5 feet that the tip of the minute hand moves every minute on Big Ben. All right, that concludes our lesson today, and hope you took good notes and did the notes must do, and we'll see you next time.
Thanks for watching.